All right, schoolgirl, so here's a special just for you, you little brat. You're so lucky. I should get paid extra money for doing this. So this is group quiz questions 5, 6, and 7. And the first, so what we're doing first is what's called dissociation equation. So we're showing the dissolution of solids in water. So the first one is sodium carbonate. Now we know that sodium is +1, and we know that carbonate is -2. So that means Na needs to have 2, CO3, and this is a solid to begin with before we dump it into water. And when we dump it into the water, it's going to dissolve. It's going to ionize. So we end up having 2 NAs, and then let's put the little AQ there, plus 1 carbonate. Again, we have to put the AQ, and we have the -2. There it is. It's as simple as that. That's letter A. B, we're going to do the same thing. Now, I want you to do this one, but I will tell you that it's lead 2 nitrate, so that means you have Pb2+, and nitrate is always the same, so it's NO3-. All right, so I want you to first combine these two things into the solid ionic compound, and then I want you to perform the same thing that I did right here for that fella. And then for C, I'm going to do this one for you. We have iron 3 chloride, so iron is a 3+. The chloride ion always is minus. So when we combine this properly, it's FeCl3 solid, and that breaks up into 1 Fe3+ AQ plus 3 Cl minus AQ. So there we have it. Those are the 3 different dissociation equations. Now, here's the thing that's kind of cool. If I put in 1 mole of this stuff, or 1 mole of this stuff, into 1 liter of water, we know that it's going to be a 1 molar solution. If you look at the question, that's what it says, that I've created 1 molar solutions of each of these compounds. Okay? However, when you take a look at this top one, you'll see that even though I start off with 1 mole of sodium carbonate, in the end, I produce 2 moles of sodium ions in solution and 1 mole of carbonate ions in solution. Similarly, if we go down here and look at the iron 3 chloride, we can see that from 1 mole of iron 3 chloride solid, I produce 1 mole of FeCl, of Fe, right? You assume that there's a 1 in front of the Fe there, of Fe ions, and 3 moles of Cl minus ions. Now, that's going to be a very important thing to understand here, because if we then go to question number 6, question number 6 asks, which of the 3 solutions above has the highest concentration of ions in solution? So I'm not saying the highest concentration of the original solid before it dissolved. I'm saying the number of ions. And you can see here, even though I started with the last one here, with 1 mole of FeCl3, I actually produce 4 moles of ions altogether. The 1 that you would have here plus the 3 that you have here, so 4 moles of ions dissolved in solution, as opposed to letter A, where I have 2 plus 1, or 3 moles of ions that would be found inside that solution. So obviously, if you're just comparing those two, A and C, then C is the one that has the higher concentration of total ions in solution. And you'll have to see whether or not B is going to be higher than that, but I'll let you figure that out. All right, so question number 7 then is a lot more complex. This is a concept called creating the complete and net ionic equations. And it looks somewhat like just doing a simple double replacement reaction, but it's a little bit more than that. So we're starting off with 2 things. First one is lead nitrate. Oops. So Pb, and actually it's lead 2 nitrate, just like what we had in the problem number 5. So lead 2 nitrate means it's PbNO3 2. Oh, I'm doing the question for you. Jeez, that's just not fair. Anyway, that's if you didn't know, that's what you're going to need to do right here, you rotten child. So PbNO3 And that's going to be dissolved in water. So we have to start off with it in solution, so it's AQ. And we're combining that with ammonium sulfate. And ammonium is NH4 plus, don't forget, and sulfate is SO4 2 minus. So I have to put two of those guys. Oops, stop. Where's my undo? There, SO4. And that 2 is going to be aqueous, right, because I'm going to dissolve that in solution. And that's going to form, we're going to do the double replacement reaction. So I'm going to do Pb, which is a plus 2, with my SO4, which is also a plus 2. And I'm going to do my NH4 with my NO3. Those are, it's the NH3, I'm sorry, NH4 is plus 1, NO3 is minus 1, so they combine in a 1-to-1 ratio. Now, of course, we do need to make sure we balance things here, and to balance it, I'm going to make sure that I put two of those guys there, and now we're happily balanced. But if we didn't put the balance, if we didn't do that, we'd be in trouble quickly. Now, if we looked at a solubility table, we would find that PbSO4 does not dissolve in water, so that becomes a solid, whereas the ammonium nitrate is definitely soluble in water. So there's the double replacement reaction, something that you're used to from way back in the beginning of winter term. But that has nothing to do, well, of course it has something to do with what we're doing, but it's not even remotely close to being done here. Because when you're doing a complete ionic equation, you have to blow apart, you have to ionize all the things that you have in this equation. So instead of being PbNO3, you have Pb2 plus AQ plus 2NO3 minus AQ. And I got that 2 because of the subscript of 2 here, which gets converted into a coefficient of 2 when you blow it apart. Okay? And then let's continue to go. Plus, I have 2 NH4s, and those, don't forget the charges associated with that, plus 1 SO4 2 minus, also AQ. And then that leads to the PbSO4, whoops, stays a solid, doesn't dissolve. So there you go. It just stays like that as a solid. But then we have the 2 NH4 pluses, AQ, and that 2 is distributed to anything that is in it. So it's not only going to just be for the NH4, it's also going to be for the NO3. And so we have 2 NO3 minus AQ. Wow, that does not look like a 3. Let me fix that little fella right there. Oh, there we go. Okay? Oh, close the parentheses. So that, what I've just written out there, is my complete ionic equation. If I'm going to do my net ionic equation, it's as simple as doing this. You cross out something that's found on both sides of the equation. It's very Hess's law-like in this way. So I have 2 NO3s, they can both go. I have 2 NH4s, they can both go, and nothing else, right? I have to keep everything else. So once I've crossed out everything, then we just bring whatever is left together. So we have the Pb2 plus AQ plus SO4 2 minus AQ, and that leads to the production of PbSO4 solid. That's the net ionic equation, and we are done.